you can use this rattle if you want, and I think that could be useful. See, it is a screening for like exploring data. You can use it. Yeah, so a lot of this as point click, you can get a result. Because what you want to do probably will not be limited by what this UI can do. You probably want to do more than that. But anyway, you can modify the commands that is, that is produced by point clicking these things in Rattle. And I'm not sure if you try to look into Rattle. There is a place that you can do some analysis about missing value. For example, you can plot correlation plot of missing values. That's the interesting thing. You can look at that. The first case I saw exercise. So you can start using like R Commander or Rattle. And I know some of you come from engineering schools, and there's R for Excel as well. Okay, and the video is available for that. Oh, did I make a link on that? Probably. I hope I didn't. This is our video tutorial. Oh, not here. I'm going to update this page, the links page, and there's a app for Excel users, so you can download that, and then you can actually run R from within Excel or the R program. So it's really interesting, add-on package, and they also have, I believe, it was like half-hour video about using that. So I had that link before, but I didn't put it here. So I'm going to try to find out and put a link on that. Okay, anyway. Oh, okay, I kind of skipped something last time, isn't it? Oh, I skipped on the Node 07.R, but not this one. Right? Except that I made a change on that, so somewhere. That's the only change I made for that class. Remember I mentioned about sub-I, so you don't have to mean that. I don't have to mean that. Anyway, so here we're going to talk about other method in the supervised learning tool. This is Node 7.pdf. And let's look at this naive Bayes classifier. Again, this is based on Bayes rule as well. Okay, and basically, remember earlier we mentioned about this. Okay, the posterior probability. Okay, meaning that after you observe your data, you try to revise your this class probability, right? Posterior probability. Okay, based on evidence. Right? Okay. It's proportional to the prior the original class probabilities. Either it's a priori or based on the sample, just the sample proportions. We don't know that later. And here, this is based on that prior belief. What is the conditional distribution of your data? Okay. Of course, we have seen linear discriminant analysis, quadratic discriminant analysis. Both are built upon normality assumption, right? With linear discriminant, we have additional assumption about covariance structures being equal. Okay, so. But here now, usually when you have more dimension, the higher dimension, that is your feature vector is high dimension, means a lot of input variables. Okay, and usually this one is hard to come by, very hard to estimate that value. Okay. So that's what this naive Bayes is about. It has this very unrealistic assumption Okay. The naive Bayes classifier, assuming that the joint conditional distribution, condition on whatever the prior come up, okay, condition on what you believe, okay, the class probabilities, they are conditional independent over that the prior, okay. So that is really a strong assumption. Okay, independence is really strong assumption and very very hard to justify. Anyway, and based on that, naive Bayes classifier can be easily computed. Okay. So here, by doing that, you break the curse of dimensionality. Each one of these conditional probabilities is only one dimensional, so it's really easier, much easier than trying to compute this high dimensional conditional probability. So only the only thing you need to do is just try to estimate individually for each variable in the feature vector the univariate conditional marginals for them. Okay? That's all you have to do. Okay. So if that is the case, then we have this so-called naive Bayes classifier. Okay? Of course, the cross probabilities, whether it's a priori assumption like a normality, or even normality, you can somewhat evaluate, assess whether normality is appropriate or not by looking at the outcome right from the data. Okay? You have some like belief system assuming that you have this a priori class probabilities, then that's it. Otherwise, okay, the class probabilities will be based on the data set. Okay? That's why it's also important when you have the entire data set, you want to split into trend data set and what's the other one? Test data set. Okay? The splitting is also important. You want to split in a way that the trend set is more or less like more representative, right? Okay? To make sure that this is true. Otherwise, when you estimate this class probabilities, it will be biased. Okay? So anyway, but suppose you use relative frequency to estimate. So here, this is a total number of observations, and then here, basically look at. Let's suppose we have a sub I here. Otherwise, doesn't make sense, right? Okay. So P hat of pi sub I. So for the I class probability, will be estimated by number of observation in class I over the total sample size. Okay. Okay. And then the estimate of this univariate marginals based on that strong condition can now be estimated by this. Okay? To observe a particular values in class, say K for the case one, okay, AIK. Okay? In class I, basically it's just observe how many belongs to that type of object and divided by the class size. Then I would be the class size. Okay? So that's very simple estimates. That's why this. Of course, the current here this is suppose you have discrete distribution. Okay, you have discrete attributes to start with. Okay, otherwise if pi this is continuous attribute, then use a density estimation. Okay? And again, of course, you can assume normality, or you can do without that assumption. Just use a regular density estimation. Okay? Now let's look at this data set. It's really, this is a toy example trying to illustrate the naive Bayes classifier. Okay. Suppose we have this, it's been observed. I know someone come up with this interesting data set, very small data set. Okay. According to the outlook, okay, of the day, the temperature, humidity, and wind, okay. And in the past, they play tennis or not. Okay, so anyway, these are, of course, the group identities are no, either no or yes, right? They're completely no. Okay, and under this combination of weather conditions, okay, this is the result that they play or do not play. So on any particular day, they have that weather conditions and they actually play. And then you want to see that. Suppose now, for the future days, say I have new observation. Okay? So what should you make up with the decision? Are you going to play it? Okay. So Anyway, here this is an example of this naive classifier. You can make use of this data. Of course, you can also use other methods. Okay, so here the prior, since we here this not assume this a priority, whatever the prior is. Okay. You look at the data. Basically, look at the data. They are 1, 2, 3, 4, 5 nodes and 9 yeses, right? So basically, you just use that as to estimate our prior. Okay. So the chance of observing yeses, okay, because out of data of the 14 instances, we have 9 yeses. Right? So just use a class size in the data over the total sample size and use that proportion as estimate for that. Okay, for this prior distribution. So probability of yes is estimated by 9 over 14. And here we have 5 nodes, so okay, 5 over 14. So based on the data, there are 5 nodes here. Okay, so 1, 2, 3, 4, 5. Okay, 5 nodes. So just estimate. Look at individual data. Okay. So here these are the conditional probability based on the prior what you observe, yes or no. Okay. Now look at that. First look at finals. Probably is much easier. And for the outlook, okay. For outlook, okay, where the answer no, there are 5 instances, right? Okay. And of these 5 nodes, 3 are associated with sunny, 0 associated with overcast, and 2 associated with rain. Okay. As you can see from there. Okay. This 5 node 1, 2, 3, 4, 5. Okay. These 5 nodes that for the outlook variable, yeah, 1, 2. Where is the other one? Here, 3 sunnies, right? And 0 overcast. Okay. And there are 2 days are raining here. This day when it's raining, and this day when it's raining. Okay. So the estimate, so that is this probability we estimate just based on this assumption. So if variables are looked at individually, okay. So here, this is basically what do we have? This is P hat of X. Well, here of course we only look at first feature variable, right? Because they are looked at individually. So where is? One here. Just say directory. So here this is our x, right? And this is x1. So first feature, right? First input variable. Given that our class is a no here, so here given player equal no, run no space, it's supposed to be here. Okay. Anyway, okay. So here this is our prior probability, right? This is our pi I equal 1 and 2. Okay. So basically, based on that, this is estimated by the class size in this data set, and they are only for our case they are only 5 nodes. Okay. There are only 5 nodes, and out of these 5 nodes, there are 3 that are associated with sunny. Okay, so it's 3 out of 5, okay? And the rest are similar. Okay, so basically that's how you estimate this value. Okay, under the prior that the place no, we have 3 sunny days, okay, and 0 overcast day, and then here 2 rainy days, and do likewise for other variables. Of course, also do likewise for the other class as well. Okay. There are total 9 yeses, and out of these 9 yeses, 2 are associated with sunny days, and 4 overcast, and 3 rains. So that's how you get an estimate. Okay. The idea is really simple, because then with that very strong assumption of independence, conditional independence, okay, then we can look at individual variable, okay, by doing that calculation. Okay. So actually, all this information obtained from the data set, right? And after that, of course, and you can look at an instance, say see here, this is for future day. If the outlook is sunny and temperature is cool, humidity high is high, and then strong wind that day. Okay. So how should we classify? The answer is to classify as no by first you calculating this posterior probability. Okay. Remember we mentioned that the posterior probability after observing this x, the feature vector x here, right? This is our feature vector. Okay. If it is yes, it's proportional to the data condition on the prior here, right? Yes, right, the group. Okay. So here this is a sunny over given yes, and then times all these whole things here. Okay. So you can actually see that the chance that this could occur. Okay. So given the feature vector, the posterior probability can be computed as, say, sunny, given that we are in yes group, and then cool, given that we are in yes group, and then high temperature, given that we are in yes group, and strong wind in yes group, and times the prior here, right? This is prior. Okay. And now here, a previous page, we have everything here. All the ingredients are here, right? We have the prior probabilities, and then we have this data condition on the priors. Okay, so we have everything. So now we can calculate this thing here. And based on that, this is about 0.0053. And the posterior probability of no is 0.0206. It's more likely to be this, right? So your posterior probability of no given this feature vector is greater than that. But yes, that's why we classify as no. Make sense? Okay. So all based on this calculation. Of course, this is entirely just a very easy, very simple algorithm you can build in this comparison. It's built in already. So it's in this KLAR package, and I think it's also in our package as well. There are some other classification package that has this. Okay. Anyway, both are proportional to this. Okay. We don't have to do this exactly, right? So this is proportional to 0.0053, and so you can actually just calculate each posterior probability. Okay. Of course, it is. Actually, we can just stop here, right? Unless you want to calculate exact posterior probability. Okay. By this, we know that this proportion is higher than that. Okay. Of course, to calculate exact posterior probability, just add this up as in the denominator, and here is this value in the numerator. So we have everything. So the posterior probability, given this feature vector, okay, that place no is almost 80%. So that's why this observation based on this feature vector is will be classified as coming from no, right? The group of no. Okay. So here this is a example on that, and usually violation independence assumption is almost in every example, right? Because this is very strong assumption and hard to come by. Again, very unrealistic assumptions. Well, this is what they claim that this is in predicts in many applications. They found that naive Bayes perform very well even with this unrealistic assumption. And in many cases, it performed much better than those very state-of-the-art classifiers. Anyway, that's what they claim. I'm not sure how true that empirical observation is, but it is that they found in several applications this is true. Okay. And basically, the possible explanation is about these structures in the features that even out when you calculate this posterior probability. There's another this is more serious issue that could arise from naive Bayes classifier is that. Okay. For zero conditional probability problem, okay. For a class, if a value of an attribute does not appear in this class in the trend set, okay, and usually that conditional probability is always 0. So that could pose a problem. And there's a remedy for that. Okay? It's called Laplace smoothing M estimates. Okay? Don't ask me why they come up with that name. Probably M estimates. Okay, just the way, okay, it is defined, okay, with this feature. Anyway, on the numerator and denominator both add this thing here. Okay, numerator add MP and denominator add M, and then here MP is kind of defined like user specified, okay, values that relative to the virtual sample of size M. So assuming that, of course, you will observe nothing, right? But assume that you have some virtual sample, even though what you actually observe is 0 sizes, and we observe some virtual sample of size M. If that is the case, then here this is the formula to calculate that. Okay. This is what was claimed in predicates that it works pretty well in many instances. But still, it's good that we kind of use these methods and along with other methods and try to compare the result, not just rely on a particular method. And of course, what we have seen here so far, we condition on a discrete distribution, right? Okay. If you condition on well, if the conditional probability density is discrete, then we already seen that. Okay. Now, if you have continuous features, okay, well, all the feature vectors that we have seen in that example, that toy example, they are all discrete. They are all categorical. Okay. What if you have continuous features, like some numerical measurement? Okay. And basically, you can either have this parametric result, which is normative assumption. Of course, this has to be justified if you have the data set. Okay. Or you basically assume the non-parametric result, not assuming any distributional, okay, assumption that you use the kernel density estimation of feature J and the class II. Of course, we don't have to get into the detail of this. This is general topics about density, kernel density estimation. Okay. The idea of this kernel density is that they divide the range of data values in several small interval called bins or class interval. Okay. And then they just estimate how likely it is to occur within that. Okay. So, and by that they have this density estimation. Of course, it depends on how fine you divide your data range. So density estimation could be very smooth, it could be very coarse. So that depends. Okay. But let's not get into the detail about this. Okay. Let's just use the result. Okay. Okay. Let's try to look at some examples. Remember from last time, I mentioned that let's look at iris data later, because iris data, the feature vectors is continuous, right? This is continuous distribution because we have this is this sepal length, sepal width, and petal length, petal width. Those are all continuous measurements. Okay? So that is the case that we have continuous feature. Okay? Let's first look at our toy examples here, our tennis data. So let's have this tennis data. If you do not have this in your system now, basically it's from our course page in the data link. Okay. I have this here. Okay. For example, you can just download this directory and you can open this up with this tennis data. So analyze on that. Okay. Or alternatively, you can source this this tennis.r. Okay. Source this and save it in the result. Okay. To source it, I think the best way to do it is copy the link location. I'm not sure how you do this in Mac.
Yeah.
You can do that. You can copy link location, right? Okay. And Windows is just right click and you have this copy link location. Okay. And all you have to do is just in R, just source that. Okay. Just type this command. I can repeat that, of course. No problem. Right? Doesn't make any difference. Right? So copy to that with this source command. See how I did it? I type source with quotes first, and I go back and fill it. Okay? Because I want to make sure the syntax is correct. Okay? I can just do that again. Let me just show how this works. So you have consecutive quotes, either single quotes or double quotes. Okay, fill in first. Okay, and then use arrow key, left arrow key to move in there, and then paste to that. Okay, so I find this is much easier to do this way rather than just have it done. So here, then doing that, you have a tennis data. Make sure you save the image. Okay, after that, you have that. So you have a tennis data. So here, this is tennis data about this. So I have this. Fill in actually all including the target variable, all variables are categorical or factor. Okay? You can actually see that by looking at this data set. They are factor classes or categoricals. We structure it this way. Okay. So once you have the data set, then let's look at our last node, node 8.r. And suppose here we're going to use this later. Suppose you have two new instances. Okay, the one included in our class node. Okay, and then there's another one. Okay, suppose I have two new instances. Okay, first instance is on sunny day. It's a cool sunny day. Temperature is humidity is high, and there's a strong wind. Okay, that's first. Okay. And the second one is like you have a second feature vector is overcast, and we have mild temperature and high humidity as well, and then there's a weak, not strong, weak wind. Okay. So here, this is way to set your new observation. Okay. In order to use a predict facility of this naive Bayes, okay, we need to put this in the same structure as your data set, at least for the feature vector, right? Okay. So all you have to do is just put in these new instances, okay, with the character forms. So here, first observation is sunny, cool, high, strong. Second observation, overcast, mild, high, weak. Okay, but put this in character form, but just construct a vector and using the same levels as your data set. Data set's tennis. Okay. So here, just levels will be the levels for the tennis in the tennis data set of the overlook. See, when you want to extract data frame, the columns, okay, in this way, use a $, okay, operator. You can specify just enough characters to uniquely identify that. So that's why I put it. So you check from overlook, and then here this is temperature and what is that? Humidity and this wind. Okay. So they will keep the same structure as that. Okay, so let me so here this is our two new feature vectors. Okay, first one is sunny, cool, high. Is that the same data? The same example as we had? I mean, sunny, cool, high, strong. Yes, that's the same. The same one. The first one is the same one as class number. Let's try to see what happens there. And of course, in order to run this naive Bayes classifier, you need a function, right? Okay. So right here. So we run this. We have this package loaded. Okay, and it just run naive Bayes. Okay. So we run the naive Bayes modeling of our response variable. Response variable is the target variable, the last variable of interest, right? You model that against all others. So it's just that will catch all other variables. Okay, so here this is a very straightforward way to specify the formula, and without data, the data is standard data. So okay. Now by default, there's no Laplace correction, the one we just mentioned, right? Okay. Smoothing and estimate, so we don't do that. Okay. I've done this already. So here this is M estimate, and then look at this. We use a priori priors here, proportional priors. Okay. So here this is what was that? 5 out of 14 and 9 out of 14, right? Okay. So here we have priors set here. Okay. Actually, this is part of the output. And then you can look at the conditional marginal, condition on prior. And basically, this is table we seen earlier in our class note, right? So everything here. Okay. So here we have for outlook, well, except they turn the sideways. So anyway, so we have that table there. Okay. Well, we have that for play equal null. We have 0 over 5, and then 2 over 5, and 3 over 5 there for sunny, right? So actually, that is exactly what we have seen in our class note. Okay. So here, if you extract this model, extract the table path from the model, and then you can predict, okay, fitted residual result without Laplace correction. I didn't take a look on that. Probably this is the default. Okay. You can actually see that. Maybe I don't have to say threshold for that. Okay. What was that? Dot predict dot. We don't have this object, huh? Something like this predict things here. Naive Bayes. This is a sort of function definition, and by default, they have this threshold of 0.001. This is This is associated with the Laplace correction. Okay, so we have to set it to 0. So it's not default. That's why I set it to 0. Okay. Sometimes I'm kind of curious about this. Usually, their intention in this package is that they are intended not to let user change this stuff. So they are hidden from you. That's why originally when I just typed this command, we didn't see anything there. Okay. But it was this 3 consecutive columns which kind of extract this sort of unexported objects from there, so you can see the definition. So anyway, so now look at our result. Okay. So when you say predict, and then here, this is our naive Bayes, and threshold Bayes, this would be the fitted result, right? Not predicting new object. Okay? The object to be predicted is just the original data set. So that basically will be the classified result. So we can use that information. Okay? So fitted results without Laplace correction. So we run this, you can see that. Okay? This will be the fitted result. The classes, this is classified classes. And here the posterior probabilities, as you can see that. Okay. So, of course, will be classified accordingly. And after that, we have this result, the fitted result in NP, and you extract the class components, right? Remember, we see this class component here. This is our NP. It has two components. One is classes. So this will be the classified classes. Classify into this, okay? And here posterior probability. So all we have to do is just compare the classified classes with the actual classes, and that would be the confusion matrix. Okay. You can see that there's one misidentified individual, okay, based on this naive classifier. It's pretty good. Only one misclassified according to that Bayes rule. Okay. So 1 out of 14. Okay, so here we have this result, and you can display misclassified cases with the data. Simply just construct this. Okay. So here I take my data set. Okay, I assemble data and assemble the classified result. Okay, and also assemble the posterior into a data frame, and then I only extract those misclassified identities. In this case, we have one misclassified identity. And that's the reason why. Okay. This is under this combination in the data set. Okay. Rain, poor, normal, strong, no, and we classify as yes. In fact, it's supposed to be no, right, in the data set. But it's no, isn't it? So we misclassify this identity. Okay. So here, this is a result for that. Okay. And now remember earlier we mentioned we have this new feature vectors here. Okay. And you can use your naive classifier to predict this result. Okay. So predicted result for new cases. Okay. The first one case is the one we already seen there. We classify as no, isn't it? This is from our class notes. Okay. That's our first feature vector. Okay. The reason is because it's a high posterior probability, and we've seen this in our class note also, right? Okay. Okay, and then posterior probability for that is this. Okay. And the second feature vector with this overcast, mild temperature, and high humidity and weak wind condition, we classify as yes. So maybe next time we play tennis, you can try to collect your data, or maybe other sports, okay? And then here to predict in the future what is your action. Of course, you need to come up with a nice classifier. Okay. This is an interesting example, isn't it? Now, suppose we do this naive Bayes with some Laplace correction. Okay. So here, basically, to specify that, this is how it's supposed to specify FL equal 1. I guess we can use a help documentation of that. I guess I have to use a help that HTML because I set it to text. So here with naive Bayes classifier, FL, this is a place for Laplace correction. Okay. No correction and 1 for with the correction. Okay. So anyway, so this one is naive Bayes. Okay, with this Laplace correction. And then here we have this proportional priors remain unchanged, and then adjusted conditional marginal. Okay, now it will be different. Okay. See, previously we see some 0 probabilities, right? So because that's basic. It doesn't appear anywhere in your data. Where was that? That's not earlier before. Yeah, we have 0 here. Okay. So here we try to use this Laplace to smoother and try to see if the result remain unchanged. Okay. So we have this result. Okay. So if you look at it now. All these conditional marginals are non-zero, okay, because of that correction. Okay. But actually, that doesn't for this example doesn't change anything here. Okay. This critical result. Okay. And then. I compare with this without using threshold equals 0, so basically use Laplace smoother. Okay. And here this is with this is well, this is with Laplace smoother and this is without, okay, without Laplace correction. Okay. They are all identical. Didn't change anything here. In fact, you can see the result. Okay. You predict the new. I should see the misclassified. The confusion metric remain unchanged. So here, confusion metric remain unchanged with this Laplace smoother, and we still classify the first feature vector as no, second one as yes. It doesn't change anything. In fact, you can also use this linear discriminant, although this is less realistic because we have categorical data, isn't it? You can still try it out. Okay. Basically, what it does is like internally they will make that categorical, make dummy variables for that categorical variables, and then just print the result. We can still try it out and see what happens. Okay. This is still tennis data. Okay? It'll be interesting to look at this. Okay? Although the assumption we violated because we have categorical data, doesn't make sense at all here. Well, the result is still good. Okay. In general, this may not be correct because we kind of force that categorical variables as like coming from normal population. We actually make use of dummy variables, okay, or class variables. Okay, class variable means that you set value 1 when this class is present and 0 for others. Okay? So that's this dummy variable. Anyway, so it's not in this case. Okay. And then basically, remember this is sort of force that to be like continuous distribution. It's kind of funny you have this result. You can see, you can plot and oh, I know this is a place that we have trouble because this is completely inappropriate because we have a discrete type. I forgot about that. But let's look at the iris data. This is more appropriate for iris data because we have continuous measurement. We'll talk about that later. What was this? What is our iris data? Did I do naive Bayes? Oh, here naive Bayes. We did that in note 07. That's why. Okay, now let's look at the naive classifier that apply to the iris data. Now the measurements of the feature vector is continuous, right? So it's appropriate for this case to use naive Bayes and where the underlying distribution, the marginal distribution is continuous. So we need to use some kind of density estimation, estimated density. Otherwise, we are not able to calculate the posterior probability. Okay? That density has to be estimated based on the data. Okay. Now here, this is the iris data. So here we are fitting for iris data. We are fitting species versus all others. And just recall what we have in this data set in iris data. So it's a data frame where we have 5 columns. The last column, again, the last variable is the target variable. Okay? This is our target variable. The response we try to fit. So we try to classify it into like one of these 3 different species of flowers. Okay? And all the measurements here, the 4 measurements are continuous measurements. Okay, so here with this data set, we do this naive Bayes here. Actually, this one failed miserably. It was naive classifier. Oh, I didn't put the actual yet. So I wonder. When did I put the actual there? It's supposed to be continuations of what we have before. When did I sign this actual? Can you see? I can't remember when I did that. I did it somewhere. Long time ago. So it's a disadvantage that we didn't continue on with this example. We have to look at it. When did I do actual? Somewhere. Right here, okay. Just run this code. So then our mean here will be run perfect, okay? So here the apparent error is 4%. Okay? There are 4% misclassified identities there. This is versus 2% we have seen earlier. Remember when you use linear discriminant, we have 2% apparent error. That's the example we sent last time. So now we have to continue on this. Okay, we have naive Bayes, right? Okay. Now, based on this naive Bayes model, now we want to see okay, what flowers have been misidentified. Okay. See, they are total 1, 2, 3, 4, 5, 6 misidentified individuals, right? 6 out of 150. That's right. We have 4%. Misclassified identities. Okay. So we compare our actual identity with the predicted result, okay, from this naive Bayes. Anyone check? Did you run? Probably not at the moment. Maybe check. We'll see if Redo run this naive Bayes or not. Maybe not. Okay. So we have to rely on these packages. I know the Redo does linear discriminant, algebraic discriminant, logistic discriminants, and logistic regression. What else? They also did tree model along with that. Probably not naive Bayes. We'll see that in the future. Okay. I'm trying to assign a second assignment. We'll ask you to do a couple different methods and see classify and then compare the result. Okay. So that will be our second case study. I try to do that over weekend. Okay. So here, these would be the posteriors that associate with this individual. That's why this individual are misclassified. Okay. In fact, from 51 to 100 is supposed to be second group, right? Versicolor, but they classify as Virginica. So you can see that. Okay. With this posterior probabilities. Okay. So here, these 3 individuals supposed to be versicolor iris, and they misclassified as being Virginica. Because of that, of those high posteriors. And in fact, the last 3 groups are actually supposed to be Virginica. They misclassified as versicolor. Remember, when we look at those scalar plot metrics, you see that these 2 groups sort of entangle, right, to each other, isn't it? When we look at earlier, when we look at the last time we look at this scalar plot matrix or that spin plot. Still remember that? Remember we looked at that spin plot last time, right? Should I do this again? Probably don't have to do this, right? We've seen this already, right? It sort of entangles. It's really hard to to classify it. So this was the one that we seen last time. Sleep for 5 seconds and you do anything. Come on. Everything freeze. I didn't get anything here. Huh. Maybe I'll overlook something. Oh, no wonder I didn't run the code. Sorry. Sometimes I can forget. We are supposed to have that the graphics first. We need this. We need this command first. Otherwise. And then we do this. Change the background to this. So I'm not supposed to do this kind of background. Okay. So anyway, you can see that the two groups, basic color and magenta, they are sort of hard to distinguish, right? And so, see, that poses a challenge to many classifiers. That's why this data set is kind of benchmark for many classification rules. If you claim you come up with a new classification method and you claim your classifier is good, you must pass this benchmark. I think they probably set some kind of standards for that. Okay? And so that's why, where are we at? We should go back to our discussion now. Okay. When did I do this naive-based classifier? Okay, so here we actually look at this predict result, and then we printed these posteriors. And you can plot the univariate density by groups. Basically, there are 4 variables, so it will produce 4 graphs. Okay? Usually, the graph will just flush out. First graph appear, then flush out, and second graph. Okay? Unless you say it did something. Okay? There are ways to pause it during each graphics. Now, the other way is probably easier is just put them all together. Okay, instead of 1 graph per page, I put the 4 graphs in 1 page. So, okay, and that's done with this multiple figures row wise. Okay. Where is that? With this plot command, it's just say way to confirm page change. If you see that, just move your cursor within the window, just click on it. That's all. Okay? And they have this naive Bayes plot, okay, of the density, right? See here, this of course. Remember, by default, normal distribution was assumed, right? So that's why you have this 3 superimposed normal curve as a comparison. You can see they are quite different. And it's much easier to set apart the setosa from the other 2 groups, especially in the pedal measurement, which sort of confirm what we see earlier, right? When you see that in the scatter plot, we can see that. You can see that the setosa stand out from the other 2 groups, right? Okay, so very easy to classify and very unlikely to misclassify that identity. But not the other 2. They have overlaps here, right? Okay. Same for this pedal width, but much harder to use this to measure and classify. Okay. And this was a normality based result. Remember, assume the underlying prior is normal, right? That was this naive Bayes. Okay. Actually, this is very similar to the LDA, except that we kind of set the covariance in 0. We don't use it, right? multivariate normal, okay, will imply, well, with a multivariate normal where covariances are all zero means that you have independent normal distributions. So actually, you kind of have your covariance matrix there, but you reset off diagonal elements of covariance to be zero. So okay, that's what happens. Okay. So in a sense, very similar to either linear distribution or more likely quadratic distribution, except we reset the off diagonal elements, the covariance being zero. So very similar to that. Okay. And here, this will be a density estimate for individual one. I don't like the default. The plot legends, they put this inside. Okay. If you're really interested, you can actually modify this. This plot can be easily modified. I think it's in this plot, the naive base, I guess. Again. Oh, they didn't even put this out, huh?
Capital R.
Huh?
Capital R.
Oh, no wonder. I thought I changed it. Oh, no wonder I put a caption. Yeah, it's a. We know how to modify. Okay. Actually, it's in the legend box here. They by default they have this thing here. Legend plot equal true. Okay. And you can modify to let user have a choice to press legend plot. It's very easy to modify that. I'm not trying to get into that thing. I probably can suggest them to change that because the way like this is not so easy to see. But that's the default anyway. Of course, if you understand that, probably you can just place the overall legends to this anyway. So, but well, let's go back to our discussion. Okay, that's not really important. Okay. Now, the next thing is that suppose we are not imposing a normality assumption. Okay. Probably this is not right. If you look at a scalar plot, okay, some of this kind of sort of not exactly normal. Okay? Well, I didn't produce a scalar plot at the moment, so maybe we can look at just go back and check the scalar plot. Okay? So here, suppose we use the kernel density, not assuming normality. So underlying distribution is some kind of distribution as long as the marginal we have independent marginals, right? Suppose that is the case, okay? And then here we plot the result. So here this is our original one. You click on that, and then we have this new result shown here. Okay? So it's just a density estimation. Still, we can see that feature here. It's really easy to estimate. Okay? Of course, this kernel density, the smoothness of this kernel density estimation depends on how you classify it. There's a way to change that. Okay? At least this tells you that it's with these two measurements, payload width and payload length, it's really easy to separate Setosa from the other two. Okay? The difficulty lies in separating these two species. Okay?
And this is when you're not assuming normality?
No, this is not normal. Okay.
Okay.
Just use some density estimation.
The results look almost the same.
Yeah, almost. Well, of course, you have to, when you use normality, you have to go back and assess normality. Look at these three classes where the data appears to be normal. I think we have that. We have that. We have the scalar plot before, right? With that scalar plot matrix, we can actually look at it. And where was it? Okay, we have this, right? Require this lattice extra, and then here run this on here. And we have this result run. Can you tell that which data set that appear to be at least bivariate normal? See, by very normal, we're looking for the data clouds appear to be no more like elliptical, right? Maybe it's true, but hard to say for this Virginica maybe. So how about in the payload width? So the measurements have to. Well, this looks like elliptical. But of course, this is only for bivariate measurements. Okay, you have to look at multiple measurements to look at. I try not get into the assessment of normality at this moment. Okay, there are ways of doing that. Okay, but anyway, both if we use the both method, they reveal both like the same observation we see here. Okay. I think it's hard to go back and forth like this. Okay. So we are here, right? Okay. For the iris data, we plot the result. Okay. And now look at the error rate. Okay. Error rate is 0.04, same error rate, and these are individual misclassified. Okay. Because you can use a table to do that, right? You can table this result and see the confusion matrix result table. Let me change this. I forgot to produce a table here. So here, these are this is a confusion matrix. Okay. The actual identity. Okay. For that, actually, we have no trouble at all with the Setosa, right? Because it's clearly separated from the other two groups. But here we do have like 3 misclassified versicolor and 3 misclassified Virginica. Okay, so that's an example about this naive Bayes rule that we apply. Let's go back to our discussion now. Okay. Now here, this pose for the next method. Okay. Well, our simple linear just linear regression model can be used to fit try to do the classification. Okay. Except that, of course, our response variable is categorical, right? And what this does is use a simple idea that for classification response Y with K classes, you basically just produce the indicator variable or the class variable. Okay? Some in the AI community they call this class variable. I don't know why it's kind of confusing. It's indicator variable. Okay. So here, basically for each class, you produce this indicator variable. For our iris data here, the indicator variables will be like this. Remember earlier that here, the first 50 observations is for this Setosa, and the next 50 will be for this versicolor, and the last 50 will be for what was that? Indica, right? Okay. So here, when you create this class variable or indicator variables, I would like to call indicator variables or indicator matrix. Okay. Suppose the first column indicator variable we want to create is for Setosa for this group, and you have all 1 here, okay, and the rest will be 0, so all 0 here, okay. And then second column we have this versicolor, and we have all 0 here and then all 1s here. So just indicating that this class is present there, right? Okay. And likewise, the last one with this for the last class variable class for that. Should I write it here? Okay. Anyway, so we create this indicator matrix, and then treat each column as a single response, right? And you can fit this response against the model, the 4 continuous variable. And the fitted response, well, each one it will produce fitted response anyway, right? You fit this column, you have fitted response. You get a fitted response using this column. Okay? But if you sum up the rows, they all sum up to ones anyway. Okay? And sometimes you get a negative value, and sometimes you get a value that is greater than 1. Whatever that is, okay? Look at across the fitted value, whichever species or whichever class gives the maximum fitted response, you classify your individual as coming from that class. Okay? So that's the idea of this indicator matrix method. Okay? So here you have this regular linear model. You just fit on the response, where response space is just sort of indicator matrix. Okay? Now usually they pose some problem. Okay? If you have a group like this, okay? This is drawback of linear regression by indicator matrix, is that you have 3 classes like this. Okay? Use this method, it tends to have only one separator. So okay? Actually we need 2 lines to separate classes, right? Okay? And most likely you will only classify as from this group or from this group, never with this group. So that's the problem with this. Okay? So anyway, the idea is that you can, if you have 3 or more classes, this could be something that you could fall into. Okay? Against linear discriminant. The linear discriminant would better separate this. Okay? Of course, with this, actually, there's one way you can overcome this. Instead of fitting this linearly only, you consider high order polynomials. Okay? That means you also find the second order term, x1 squared, x2 squared. You could also find the interaction term, the product terms, and so on. Okay? So that's the idea about this. But you can fit up to k minus 1 degrees polynomial, okay? Order polynomial. Okay? And the decision boundary basically will be based on that. Okay? We can actually find the decision boundary, describe it linearly, okay, with this result. Okay? So given any feature vector, okay, between class K and class L, if this is true, you cannot separate that feature vector, okay, between class K and class L, right? That's called decision boundary, isn't it? Decision boundary. This is the place where, okay, the 2 classes cannot be identified, okay? Because they have, in a sense, you can say they are identical in response. Okay? Well, fitted response. Of course, here this is a simple idea, but how we do this in we can do this directly in R. Actually, did I put it here? First method is just here for you to understand individual procedure, but you don't have to use that. Okay? It's much easier to use the second method. I didn't change this. Oh, okay. See, I remember I modified this class node because I forgot to take the fitted value of that. Okay, not just linear model. So I need this fitted to enclose this linear model. So y will be fitted value. Just one simple command to get everything here. Okay. Either use this or you can use the first one. You can fit the first indicator variables and the remaining. Just use the same model information to fit. To have the fitted response, and that's what is in there. Okay, I try not to get into this. Okay, this is about the R model. Probably much easier to use that because this is the indicator matrix was provided in this neural network package. Okay. And this package comes with a standard distribution, so you don't have to install that. It's there. It's already there. You have to install your R. It's already there. Okay. Of course, it's not loaded by default, so you have to either load it, use a required statement, or library statement, library mnet, right? Or require. Since this is only one-time deal, so I don't bother to attach that. So just use that indicator matrix. Okay. So basically, all you have to do is just so here this will create this matrix. You use this for neural network, 2 columns here. Okay. for neural network package and class.ind. So that's a function in that package you can use to create this indicator matrix, okay, of species. So basically create this 3 column. Okay. And exactly when you do that, they will name this Setosa, versicolor, virginica, exactly. So it's so convenient to use that, okay? Rather than doing this, okay? That's a lot of work. Okay? So just do it directly. So we are fitting just regular linear model, okay, and using the indicator matrix. So here the left hand side would be a 3 column matrix, indicator matrix, okay, fit on this 4 measurements, okay. I guess you can try just use that here, so just fit all others. I think it should work. Okay. I didn't try it out. It's much easier to specify than number, right? So I guess you can do this on the left hand side and right hand side, just put a dot to fit all the rest of the variables. Okay? Instead of writing like this, and this data iris. Okay? So when you do that, let's just do this directly. So here we have this fitted response. Okay? And let's just take a look at the first few rows. Okay? Let me look at the first 10 rows of this result. Okay? So here, these are the fitted response. Okay? So now you can see some entries are negative, right? And some entries even greater than 1. Okay? So, well, this is some problems with that. Okay? But still works. This is so. For example, for the first observation, we are classified as being from Setosa because we have maximum here. Actually, uniformly, I think you have all the maximum occurs here. That would be interesting to look at starting from like 51 and up. Okay? Let's look at a few of that. Okay? Let's from 51 to 20. It's not 20, sorry. 70. Okay? I wonder if it's wrong. Okay? From 51 to 70, remember these are the flowers coming, they are versicolor, right? And do you see a misclassified identity here? This was, right? This was misclassified, isn't it? Because the maximum occurs here, right? So we would classify this feature vector as from virginica, but in fact supposed to be versicolor. So here, this is how it was classified. Of course, you don't want to do it by hand, right? So you got to use a computer to figure this out for you. And actually, which maximum will be the command to use. So where did I put it? So let me just finish this one, and then here we are done. Okay, that's for today. So use a which maximum. There's a lot of misclassified identities. Okay. So which maximum would be the one to do a close, okay, the count, that means taking the row, okay, and apply the index for which maximum, and that will be the classified identity. Okay. I guess I think I just let's stop here. Okay. And here this one was APER of 15%, okay, with very high misclassified method. Okay. This is not a really good method, like in this case. Okay. Okay, let me stop now. Okay.